All right, there it is. Density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. That's kind of important. That's a rate. Values of f of r for selected values of r are given in the table above. Use the data in the table to estimate f prime of 2.25. Correct units interpret the meaning of your answer in the context of this problem. All right. You are trying to find the derivative at 2.25, which is between these two values of r. So we're looking at an average rate of change between those 2 points. So this is the f of b minus f of a over b minus a, and in this case your b is 2.5 minus f of 2 over 10 minus 6, f prime of 2.25, like that. All right, so you gotta, I'm sorry, this is completely wrong down here. This is the b is 2.5 and a is 2, and then the actual values come from the table. 10 minus 6 over 2.5 minus 2. So we get a number for that, 4 over 0.5, which is 8. But then we need units. So it's currently milligrams per square centimeter, like that. And then the derivative adds another unit power, so it'd be milligrams per centimeter cubed, looks like.
Okay.
All right, so moving on to part B. One of the things you might start noticing about the free response questions is that they just move a ton back and forth between derivatives and integrals. I think that's by design to make them confusing. All right. Total mass in milligrams of bacteria in the petri dish is given by the integral expression r and 2 pi integral 0 to 4 r f of r dr. Approximate the value using a right Riemann sum with 4 subintervals as indicated by the data table. So they're telling you to use n equals 4. You have to calculate what's called a delta x. In this case, it's delta r, which is b minus a over n. So your b is 4, a is 0, n is 4. So your delta r is 1. Now what I like to do is I like to write the left value a, increment by delta r until I get to the right endpoint. And because we're using a right Riemann sum, we're using these 4 values here. Meaning like the rightmost values, okay? This is true though if we're using some sort of a function, okay? Because we're using a table, which I'm about to snip in here, it's not quite the same, fortunately. They really make this a lot more complicated than it should be. The only mapping that's going to be kind of the same is that you are using these values right here, okay? But your delta r is not always 1. In fact, you can see that delta r, because you're going from the right, your delta r changes based on where you're going, because you're going from really 4 to 2.5, so your delta r there is 1.5. You're going from 2.5 to 2, your delta r is 0.5, 2 to 1, delta r is 1, and then 1 to 0, your delta r is 1 again. So it's a little bit of a like wait, I thought we did Riemann sums and they were always the same. Fortunately, in the AP, you don't get that. You get these mismatched ones. Okay. So we're going to do this integral here. Let me snip it one more time. Sorry if it's kind of all over the place. There's a lot of setup to actually doing it. Okay, so this integral right here is And I like to start from the right. So your R value is 4, and then your F of R value is 18, but you're multiplying it by the delta R, which is 1.5. So that's for the rightmost one. Plus, we're kind of working it backwards. The R value is 2.5 times the F of R value 10, and then your delta R this time is 2.5 minus the 2, which is 0.5 there. Plus, so we're working our way backwards. 2 times 6, and then the delta R that time is 1, 2 minus 1, and then the last one is 1 times 2. Again, we're just using these values here. Delta R is 1. And your 2 pi comes out here, and there's your answer. You do not, as far as I recall, you don't have to actually simplify this, you just have to set it up.
Oh, you don't?
Well, that's something to ask. I'm not currently involved in the AP, so I have no idea, but I remember that pretty distinctly because you almost don't want to simplify, is what I recall, but please double check because you can make some mistakes here. You do need to give the proper units, but that's in milligrams, so it'd be like this in milligrams, or you could simplify if you needed to.
Okay.
Any questions on that before we go to part C?
No.
All right. Now, you do not have to do these problems in the order either. Like they can get like in a lot of ways, like C is completely unrelated to B, even though it feels like, well, how can I answer C without B? This goes back to some wording in the original prompt. So it's easy to like miss. Let me see if I can right there, grab it for you. So in the prompt, it says increasing differentiable function f, like that. In that case, it's good to draw an increasing differentiable function. So here is an example of an increasing differentiable function. Notice the tangent lines get steeper each time. That's what they mean by increasing.
Okay.
So your right sum here, you start at the right side and you draw this rectangle. And you can probably start making a decision about whether this is an over or an underestimate. The area of these rectangles is much larger than the actual area under the curve. So it is an overestimate. It has nothing to do with the value you found in part B. It only has to do with the shape of the curve described in words there.
Okay. Okay.
All right. D. Density of bacteria in the petri dish for 1 to 4 is modeled by the function g. G of r equals 2 minus 16 cosine 1.57 squared r all to the power of 3. For what value of k in the interval 1 to 4 to k is g of k equal to the average value of g of r on the interval 1 to 4? So this is really loaded. Like there's like a lot going
That's a
on
lot
here.
of information.
It is. And you try to piece out the things that, maybe you look familiar to you. Like when you see average value of G of R on the interval from 1 to 4, that is the average rate of change.
Okay.
That is G of 4 minus G of 1 over 4 minus 1. So on the AP, you want to try to do something. This is something, even if you're not trying to do everything. Like if you see something you do know how to do, you try it and see where that takes you. So from the table here, I'm going to scroll up here and look at it on my other screen. Oh, I'm sorry. We get that from this here. Sorry, this equation. So you actually, this is certainly a calculator problem. Do you have a TI-83?
Yes, yeah, it's right here.
All right, so let me, I've got a virtual one. Let me pull this up and show you how to do this fast, because it can be very tiring to do these calculations. So let me pull that up here.
Wait, so you do G of 4 minus G of 1, 4 minus 1 when you solve for average value?
Yes.
But when you do average rate, is that different?
This is asked for the average value, not for the average rate. But sorry, I take that back. That's a good, I'm glad you caught that. I am not paying attention. This is not correct. Okay, the average value, glad you caught that. The average value is the integral 1 over b minus a, 0 to 4, or a to b, I should do more generally, a to b of whatever your function is, in this case, g of r dr. Calculator could still be in play here. Well, actually, it has to be in play. You're going to need to use the integration feature on your calculator. Are you familiar with how to use that?
Yes.
Okay.
Yes.
Square root of r. So you're going to use x. So this is the average value. So you want to calculate that. And I'm going to do that in another tool that I use.
Okay.
We'll compare results here in a moment. Oh, I guess you take the cosine. Oh, and then cube it. Yeah, that looks right. Okay.
I got 9.87.
Yes. Yeah. So it never tells you how many decimal places to go out. So go out a few. We'll go out 8758 on that. So that is just the first part of it. So it says, for what value of k is g of k equal to this right here? So basically now you try to figure out where the original function equals, or sorry, where the average value, which is this number we just found, equals 2 minus 16 cosine 1.57 square root of r cubed, like that. So this is not really a calculus question anymore. It's just a solving question. So some options would be to graph them both, find the intersection. You could solve it by hand. How do you think you might do this?
Chain rule or
There's no derivatives. This is just manipulating the equation. It's subtracting 2 divided by negative 16, taking a cube root, then an arc cosine.
yeah, you just have to subtract the 2, divide the 16, take the cube root.
Right. And that, yeah, so you're a do it by hand, and that's fine. So then it's the cube root of that. Then it's the cosine inverse of that. And then you multiply by 1 over 1.57, and then you square it. That equals r.
Okay, that's a lot.
And that's again where I would say, I'd probably ask my teacher tomorrow, like, I was working through a problem last night. I mean, I know I can do this in the calculator. Should I even spend the time? That's where I don't think you have to. I think you can just do this and be done with it, move on.
Wait, so we're squaring the, okay.
Yeah, the last piece to get to that is,
Oh, the whole thing we're squaring.
yeah.
Okay. I got 2.497.
Yeah, I'll take it. Again, I think you're going to be okay just leaving it like this, but sure. All right, so, exhale and realize that the next question is just as difficult, just as long. They move between derivatives and integrals pretty heavily here. All right, so number 2 here. Particle P is moving along the x-axis. The velocity of particle P at time t is given by v of t sine t to the power of 1.5 for 0 less than t less than pi times 0. P is at position 5. Second particle Q is also moving along the x-axis. The velocity of particle Q is given by a different function t minus 1.8, 1.25t. All right, there's all of that's explained. Find the position of particles P and Q at time t equal 1. So notice they're asking about the positions, not the velocities.
So where do we?
But they're giving you velocity, so you gotta recognize the relationship between position and velocity. So there's some fundamental theorem of calculus that says the position function is the initial value. Oh, sorry, go ahead.
Oh, wait, you go.
It's some sort of initial, evaluation at 0 plus the integral from 0 to your time of interest of your function v of t dt. So basically for P, how this works is for P, its position at time 1 is its initial position at 1, which is 5, P of 0, which is 5. Sorry, that's 5, plus the integral from 0 to 5, and then 0 to 1 of sine t 1.5, like that, dt. So the integral from 0 to 1 gives you the change in position from 0 to 1. You have to incorporate the fact that you were already somewhere.
So it would be 5 plus, and then can we just plug that into a calculator?
Yeah. Yep, I'll do it here as well.
Is it 5.37?
Yeah. And then you have to do the same thing for Q. Q of 1 is Q of 0. And it's good to write this, by the way. I mean, just as much of this as you put in there, the better for the grading of this. T minus 1.8. Has your teacher shown you a rubric for the AP?
I don't think so.
All right. The reason I ask is because you'll be surprised. Like you might get 1 point out of like 3 for just writing this equation.
Okay.
And that's why it's important to kind of know what they're grading for, so you know if you need to work it out or not. They're available online. I can look if you want to spend some time on that today. But go to the calculator, get this result here.
What's Q of 0 again?
Looks like it's 10. Oops, wrong screen.
I got 8.56.
Yeah, the integral is actually negative, which is fine. Like visually, like, well, I think we get into that in another problem or later part of this problem. Any questions on that before we move on to part B?
No.
Okay. All right. Yeah, that's what we're doing here in part B. Okay. So our particles P and Q moving each other at time t equals 1. So we have to start at t equals 0 and look at what's happening here. So t equals 0. Which one was that? 5. All right, P is, and this is just arbitrary. This is P is at 5 and Q is at 10. Okay. And at t equals 1, we know that what was our answers for P was at 5.37 and Q was at 8.56. So you might think they're moving towards each other. Okay, but the way you answer this is to know the direction of the derivative of each of these at t equals 1. You need to know P prime of 1 and P and Q prime of 1. You need to know whether, because you don't know whether Q is moving left or moving right. P is moving left, P is moving right. Because here's what could happen. They could actually be moving in the same direction, opposite directions, or towards each other. And that's all based on the sign of the derivative. So you want to do an n deriv. You probably have seen that on your calculator.
No.
The numerical derivative, math, not math, something. Let me look here.
Math. Oh. Yeah.
You want to do yeah, math 8.
Yeah, I got it.
You want to do an n deriv for each of these at 1. So you want to go back to, but
I did
I'm sorry.
not know we could do that.
I'm sorry, I gotta be careful here. That would be true if you had the original function. You don't have to do that because you have the derivative. So all you've got to do is evaluate the derivative at 1 and the other derivative at 1. And yes, n deriv works for if you're given a function, you want to find the derivative at a point, it will do that for you. So to just be clear here, we have to find sine of 1 to the 1.5 power. And then the second one here is 1 minus 1.8 times 1.25 to the power of 1. And we only need to know the sign of these, whether they're positive or negative. For the sine one, your mode has to be in radian because you don't know anything about degrees.
Okay. So for the sine one, I
Yes.
got 0.84.
Okay, so it's positive, so it's moving to the right.
And then for the Q, I got negative.
Yes. So it's moving left. So they are moving towards each other. But to just say that because at some snapshot at 0 and 1, that they're now closer together means they're moving towards each other, you really should verify it with the derivatives that tell you the direction it's moving.
Okay.
So we will get to use n deriv for part C, thank goodness. Find the acceleration of particle Q at time t equals 1. Is the speed of particle Q increasing or decreasing? So the acceleration is the derivative of the velocity. So you're going to use n deriv in your calculator there of the velocity function. So the velocity at Q is t minus 1.8 times 1.25 t. So this is where we're using n deriv of that function and then evaluating it at 1. You want to give that a try? I'll do the same thing in my other tool here.
And then you find it at 1.
Yes.
I got 1.026.
Yes. So here's what that means. It means the derivative is positive. Okay. So you have, and we got to be careful because it's the derivative of the derivative, but the velocity of Q at 1, we did this in the previous problem. The velocity of Q at 1 is negative. Let me do it this way, is less than 0. The acceleration of Q at 1 is greater than 0. The only time a particle is speeding up is when both these have the same sign here. Okay, so typically it's like v greater than 0, a greater than 0, but it could also be that the velocity is less than 0 and the acceleration is less than 0. It's slowing down when they are opposite in sign. So v greater than 0, but
So
acceleration is
it's
less than 0.
slowing down.
Yeah, decreasing, if you will. When it says explain your answer, it's not looking for words, it's looking for symbols. It's looking for you to say VQ less than 0, AQ greater than 0, slowing down. Like they don't need any sentences unless it says interpret. You don't have to write anything.
Okay.
Okay. Ready for part D?
Mhm.
Let
Is
me
that
know.
just like the integral?
Kind of. This problem is asking you to distinguish between total distance and net change. All right, so the integral is net change. Total distance is the absolute value. So this would be like f of x. The total distance is the absolute value of f of x. Basically, you have to take into account pluses and minuses. So I don't know if you remember that, but imagine like something that is both positive and negative.
Mm-hmm.
The total distance adds these, whereas the net distance adds and then subtracts them. It's the distance, it's the difference between like you're running around a track and you get back to where you started, so you haven't gone anywhere, or no, I've run an entire lap. So having said all that, how you answer total distance in an AP exam is it's the integral from 0 to pi of your velocity function, which is sine t 1.5, but just for safety, you put it in the absolute value. What that does is it turns any negative areas you have to they become positive. So like if you had a graph like this, the absolute value turns it into one that looks like that. So it's positive. Basically, all you do is add absolute value in your integral.
How do you plug in absolute value in the calculator?
It's math something. We gotta look. Math num, the first option.
Okay.
ABS. Now, since you only care about this interval from 0 to 5, it's not asking for its position, so you don't have to include that first part. It just wants to know how far it went from 0 to 5.
Okay. I got 1.93.
Okay. And you'd probably want to give units. So this one is unknown. They didn't give you units. Interesting. They should have. Anyway, looks good. So like I said, we definitely don't have time to go through everything. Do you want me to transition to any problems or just keep going through them in order?
Just keep going.
Okay. All right. All right. A company designs spinning toys using the family of functions y equals c times x squared 4 minus x squared, where c is a positive constant. Okay, that's nice. The figure above shows the region in the first quadrant bounded by the x-axis in the graph of the function. All right. Each spinning toy is in the shape of the solid. That's interesting. Solid generated when a region is revolved around the x-axis. Both x and y are measured in inches. Very good. Okay. Find the area of the region in the first quadrant bounded by the x-axis in the graph of y equals cx square root 4 minus x squared for c equals 6. Okay. So this problem is asking you to find just the area of this piece right here. All right. So here's what you don't know. You don't know the value there where it hits, but maybe you can figure it out. Right? Like normally you need an a to a b. It's the integral from 0 to something, 6x square root 4 minus x squared dx. But how would you figure out where this hits the x-axis?
Like make it equal to 0.
That's right. You're going to set 6x square root 4 minus x squared equal to 0. You're going to set 6x equal to 0. That's the one over here on the left. Square root 4 minus x squared equal to 0. What do you say on that?
So x equals 0 and x equals 2 or
Well,
negative 2.
yeah, we want the positive one, so we'll go like that. This is another thing that I don't remember. It'd be good to ask your teacher. We could look it up. Is like right here, can you go to just your integration? Like, or do you need to do this one exact? This one does work out where you can do it by hand, but I don't remember if you need to do it all the way. So at a minimum, you got to put in your calculator and get the integral of this area under the curve.
Okay, wait, I have to plug it in. I got 16.
Yes. All right, so that's part A. Because it worked out nice, maybe just go with the calculator and you don't have to worry about what I just said. Next part here. All right. It is known that the derivative is this. They're telling you the derivative. You don't have to calculate it. For a particular spinning toy, the radius of the largest cross-section, the circular slice, is 1.2 inches. What is the value of C for this spinning toy? Any idea how to proceed from here?
No.
Okay, so it says the radius of the largest cross-sectional slice is 1.2 inches. What do you typically use the derivative for?
The
In op
rate?
it is the rate, but in optimization problems, what was the derivative done for?
Like absolute max and min.
Yes. So
So
so you set the derivative equal to 0 typically.
I set the derivative equal to 1.2.
No, equal to 0. You set the derivative, like normally you set the derivative equal to 0. Think back to an optimization problem. You take the derivative and you set it equal to 0. Okay.
So
They're telling you when you set it equal to 0, they're telling you what optimizes it.
that would be x.
Yes,
So then we solve for C.
that's right. Now, the shortcut here is to remember that the denominator doesn't contribute at all. So you're just setting the numerator equal to 0.
Okay.
Sorry, this isn't quite right because this is not going to work out the way I want. Sorry, no, I misread something. This is referring to something else. Figure this between X, Y. Radius of the largest cross sections. Okay. I believe, sorry, this won't work. I got to take this back. I misread this. So the Y value is the radius. Just think about this for a moment. What is the value of C for the spinning toy? 2 slices. Okay. I believe they're referring to this. There's an X value where it gives you 1.2 inches as the Y value. And I believe they're asking you to do some sort of a substitution here to solve for this. But how would you know that? Because you'd set that equal to 0. Okay, so I believe what you do, going back, I believe you do have to set this equal to 0, the numerator still. 4 minus 2x squared, set that equal to 0. And you find that x equals plus or minus the square root of 2. And that is what, and you know that it's the positive one. Let me say it that way. And because you want the largest cross-sectional circular slice to be 1.2, the Y value is the circular slice. Like if you go back to the graph here, the Y value up here is the 1.2 is what they're referring to. So your x value comes from the derivative. You put that back in here and here, and you solve for c. So c is 1.2 over x square root 4 minus x squared, and you have the x value, which we'll supply here.
Okay.
So 1.2 over square root of 2, square root of 4, minus 2, which works out nicely, believe it or not, 1.2 over the square root of 4, which is 0.6 equals c.
Wait, how'd you get square root of 4? Oh, wait, I
Yep.
get it. Is that what only thing we're solving for?
It just asks for the value of c.
Okay.
All right, part c. So this is kind of that, okay, we were using derivatives, now we're going to integrals. For another spinning toy, the volume is 2 pi cubic inches. So the volume refers to spinning that original graph here over the x-axis. Okay, let me snip that in here. So this is after it's done, after the revolution of the solid, they get the known volume. So from your class, you had some sort of formula for volume. This is a disk method. Does that sound familiar to you?
Yeah.
Washer would be if there was kind of something in between, or the donut, kind of like the donut method. The disk is solid all the way through. So it's the integral from whatever your start, 2 pi times the integral. I'm sorry, not 2 pi. That's a different one. Pi r squared. And your radius is the y value. So in this case, your radius is the cx square root 4 minus x squared. And we already know that it goes from 0 to 2 because we solved for that in part A.
Mm-hmm.
So 0 to 2, pull the pi out, cx square root 4 minus x squared dx, and then this is all squared.
Can't we plug in for C?
We don't know c in this part.
Okay.
It says to determine the value of c, so you can't rely on any of the previous calculations as much as you would like to. That may be why it's there, because they want you to think through that. The volume we know is 2 pi. That's good. All right, so before we do any integration, I would recommend canceling out the pi's, okay? And then the other thing is that this square here, it applies to the c squared. So the c squared is going to be on the outside, and it's not worth simplifying this part. Dx from 0 to 2 equals this. So in terms of like how you get c, it's just an algebra exercise now, but your c is based on this value, this integral, and then it's divided 2 divided by the value of this integral, the square root of that. So c equals the square root of 2 over the integral from 0 to 2 x square root 4 minus x squared dx.
Okay. Where'd you get the 2 in the numerator from?
Over here on the left, you're
Oh,
like, think of this integral as a number, whatever it is, you're dividing by it, and then square root of the whole thing to find c. I guess it's plus or minus. I don't really know if that matters.
okay. Okay. And then D.
So there is no d. I think that's it for number 4.
Wait, is there no D?
No, not that I can see.
Oh, okay. Do you want to go to the next one, or do you just want to call it a little early?
It's up to you. You're the customer, you tell me.
We could just call it early because there's no point in starting number 3.
Got it. Yeah. And you can see that this is about the speed that we can go through